Hey, I'm live again. So I was going to install software on my laptop to try to do the go live from there, which offers a lot more options and scheduling stuff. So still working on that. It is a interesting laptop setup. So I'll get back to that someday, a couple years. So I'm going to put a link down below to a great conversation the Non Sequitur show had last night with a fellow named Ayel, who was trained in Israel on some pretty sophisticated and advanced electronics. And listening to him, um, he went through parts of education and training I had in both the Marine Corps on radar systems and its air command schools or DoD schools for metrology and instrument calibration services. So it was just amazing to hear him speak with confidence about what he's doing, what we're doing. And it goes into my last note was I was going to talk about calibrating satellites, which is fascinating in itself. But he's speaking to microwave measurements, um, and how you can use microwaves to measure ocean surface information. Okay, he also mentions how light can bend. So, using a laser for checking a distance for straightness or parallel can be deceiving if you don't know what all the rules are out there. And this is some of the bad science that people use to make other claims that are not right. So, kind of why I'm here, I'd like some feedback about the live stream. I think I put down Sunday at 8 a.m. Pacific time and see where this goes. Or I wouldn't mind being invited to speak with somebody else. Um, it would be hard for me now to host a live stream, so that one's kind of tough to do other than the text interactions, so stuck with a cell phone. So again, I'm going to put that link, again, a conversation with Ayel about how we measure ocean surface information. And it's just one aspect of how we measure ocean surface information. So in the later part of the show, someone came in all belligerent because they didn't understand half the conversation. And IL spent a lot of patient time trying to catch him back up to either what he didn't understand or he missed. But the feigned indignation that the other caller offered was, I, I don't get it. You learn, that's the best thing you can do. It's good to challenge if you don't understand, but my gosh, he missed a whole lot of what had been spoken about, misconstrued it, misheard it. So you almost have to go back and listen a second time, and I hope whoever the caller was does. And he ended up closing rather nicely, but he came in with an attitude big time instead of a conversation. And he was wrong. So great. Like I said, what IL talked to was the science we use today to look at the Earth. The reason I'm talking about satellite calibration is after looking for a long time at the detector physics for satellite imaging and what those capabilities are. Now, detectors are pretty specific. They can be optical detectors, so they work with photons, detecting photon energy. Others work with electromagnetic energy, microwave, radars, which is usually above even microwave frequencies, but it all depends. Um, what you're looking for. So there are thousands of satellites up in the sky that are taking images of the planet day in and day out. And there's a whole satellite upload download system built across the planet involving every government that wants to get information from satellites. They have to schedule time sharing because there's not enough bandwidth for all the satellites up there. So it all gets scheduled, or more receivers get built and added into this reception array because satellites move. So a satellite, no matter what type of detectors it has on it, okay, and they can be high energy detectors. So they're looking for alpha, beta, gamma, um, what you would call microwave background radiation type of things, and other high energy particles that give you elemental information about what's going on out in the universe. Well, we have those satellites looking at the planet too. And what we learned from that is sorely lacking because we've been doing it for so long. The satellites are telling us how much vegetation is on the planet, how much sand and dirt is on the planet, how much water, what the temperature of the water is, what the constituents of some of the water is. So, what's happened over the decades is we have just gotten infinitely better in precision and accuracy on how we measure things. So, it doesn't take as much energy to measure because we've got more sensitivity. So, you don't have to do as much harm with some types of spectrometry, like geological sampling, where you have to create a loud thud and listen for the echoes of that very low frequency thud. So even low frequency matters. How we measure low frequencies earthwise is not satellite based that I know of, but could be. So yeah, satellites are doing a lot up there. But let's take one satellite in orbit. The satellite is going to be very specific in its spectral capabilities. So if it's optical emissions, photons, light, visible energy spectrum, and that's what you need to go look at because that's all that specific detector on that specific satellite can see. Once you have that definition, you can learn what information it can extract. So is it seeing CO2 in the air? Is it seeing uh, dust particles in the air? Is it seeing sulfur in the air? So each one of these compounds has some pretty specific interactions at pretty specific frequencies. And if we know about them, we can use this in very detailed analytic techniques to figure out what that is in the atmosphere. So somewhere I put out an earth.nullschool.net link. And if you look at the background of that, it is an open source piece of software. And basically clicking on the icons on the front page, you can open up the about and settings and everything else. But that database goes back to GIS data, or that application does. And that GIS data, Global Information Systems, I've got a video I haven't shared on that, but it's confusing stuff. So GIS is global is a global information system. So any data collected against it has specific attributes about when and where it was collected, so it can be compared in time to anything else that happened at the same time. So a detector on the east side of the planet and a detector on the west side of the planet that see something at the same time, even though it's 3 p.m. here and 4 a.m. there, they correlate that data, put it together, and make some sense out of it. So what data are they getting? We're going to go back to that specific satellite. This one's looking at optical emissions, and for conversation's sake, it's looking at foliage spectrums because we know that plants reflect light at specific wavelengths. So that's what makes a leaf green when you look up in the sky and the sky is blue. So the leaf is doing some photochemistry that's telling a story about the surface of the leaf, and we can see that from a satellite. Now, if that doesn't make you think a little bit, it's about perspective, it's about resolution, it's about camera geometry, it's about detector physics, it's about data processing and timestamps within milli, micro, or nanoseconds of each other in order to be able to do, I'm going to call it interferometry or spectrometry analysis on the data sets. So satellite flies over and collects a whole bunch of data, and then it flies over another day and collects a whole bunch of data, only its path is slightly different, so it's trying to do mapping. And a week later, that satellite's still collecting data, and it's got a bundle to download. Now it's in satellite distance or whatever, deep dish distance, and they can unload all that data with the timestamps, with the location. They know what the satellite was looking at, and now they've got a huge data set. So what does it mean? Well, they know detector physics and geometry, so they know what the data is supposed to be, but they don't know how accurate it's supposed to be. And this is where calibration or certification comes in. On the ground, or in the air, or even another satellite can help to certify or calibrate the information that is sent down from that one satellite that passed over. The ground stations are huge, typically acres or even larger arrays of weather and atmospheric sensing instrumentation. So if a satellite passes directly over that, the information relayed back to the ground station for that specific time instance can be compared. And whatever the ground says is considered the standard because it's there. It's not an inferred measurement like as you get from satellite microwave or optical interferometry. So all of this matters. I never worked on any of these things by myself. There was always a body of knowledge in books and manuals and details well beyond. When the service tech walks in with a stack of books, that was me. Plus, I had an internet connection to more stacks of books and a phone connection to stacks of minds in offices back in Boston. So, you're kind of never alone in this. And if you know the questions to ask and who to ask them of, um, it's kind of easy to get an answer because the person that's hearing the question understands what it means and can either say, no, that's not relevant, or yeah, go fix that. Check out the SCR bank, or whatever. So that ground verification of a data set from the satellite can be used to judge instrument drift. So if the satellite's instrumentation drifted or does drift naturally because of, say, sunlight access, when the satellite is behind the planet in shade, the temperature variance makes reading measurements different, and the satellite can't correct for all of them, so it can correct for the data if it knows what the reaction was to the temperature changes. So you can go back with the right information and correct collected data based upon what you know about the status of the detectors inside the instrument. Now, as you can imagine, this means a memory of what this thing was last week, what it was a month ago, what it was the last time it crossed over a calibration station, versus maybe two other satellites that are in a synchronous orbit with this, that you might be able to compare data. And those comparisons are actually done. These are massive data sets from hundreds of satellites and hundreds or thousands of ground stations, and even weather balloons, aircraft data. It all gets inserted into data sets that the National Weather Service uses, that the FAA uses, that every single weather station on the planet uses. It is shared data. It's across the globe. Look at earth.nullschool.net. That visualization is probably one of the best you can find. The source code is open. You can go read the source code. If you got a question, come back and I'll confuse you more. The data sets are open. That's kind of the amazing part. If you look at the data that it's processing or can process when you go back in time, some way cool information is there. So that was a satellite view of how a satellite data set can get transformed because of other statistically relevant information. The data can be discarded as bad because of other statistically related information. Any changes would be a matter of record somewhere in a chain of custody. The challenge with those is, over time, this data has been migrated from decades old systems, and the rules for the data back then, even the methodology for the data collection back then, might not be applicable to today. So you'll see that in radiation measurements or temperature measurements, where you go from Roentgen to sieverts, you go from pascals or temperature measurements, you go from Kelvin, which is an absolute scale, to either centigrade or Fahrenheit, which are relative scales. And those conversions can mind boggle. So, but they're all done. They're done automatically in computer systems after people have looked at what the conversions are supposed to be and says go, and gets them applied. So data gets translated. It comes out of old relational databases that no longer exist technically, or archive databases that were built off of versions of Oracle, long gone, built off of Paradox, long gone. There's ways to move all the data around if you have the history of the data. So now, there is a new video out on how we use Earth satellite arrays across the globe to talk to these satellites, because they're not stationary and the Earth isn't stationary. So we have to grab bits and drags and pieces of data and then move it somewhere else for storage, and then look at it, and you don't see some of these outputs analysis for years, because new data can mean old models have to be changed. And what does that mean? All right, supercomputing infrastructure. One of the biggest challenges in supercomputing was the evolution of computers and the hardware structures inside of them. Bus architecture, word standards, word sizes, even the errors introduced, because the math in some supercomputers had enough error to be able to cause problems with long integer calculations. So if you know the problems were out there, you can make reasonable adjustments and assumptions to the data. You can change error bands and bars around the data, which most people don't get to look at, or don't need to, depend on presentation layers, right? Who your audience is. So that's almost at 20 minutes now. This was meant to be short. again in the comments or somewhere. If you want to try to link up, let me know. I put my email address in the About section. Discussions are hard to get to, but there's a way of looking at it. So, yeah, so this is what I've been studying for 8 years, from particle physics to elemental chemistry to, but I've been studying the papers and the studies behind them. So you notice little things in physics that get mentioned. One of the studies, I'm going over my 20 minutes here, eh? One of the studies that was done in the 80s was particle, elemental, and particle migration through permeable membranes, let's say. And guess what? The Earth is a membrane, the surface is. And it acts very much like a fractioning column or a capillary column in how things move about. And you have to put this into billion-year perspective to understand that crystal that grew. It took a long time to grow to get here. It's older than you and me, knows more shit than any of us ever will. The it's interesting stuff out there, and I lost the direction I was going in. So understanding the depth, the history of science is kind of important to understanding where we're going to go, what we can do with it, and what we should. Maybe if more people appreciated that, spot on. Hey, don't stick three-letter words where they don't belong. Thanks.